Hi class, welcome back. Today we're going to talk about Rolle's theorems and the mean value theorem. These are two important theorems, and we're going to be referring them throughout the semester. So our objective is to understand and how to use Rolle's theorem, and also how to understand and use the mean value theorem. So before the Rolle's theorem, we had this theorem called the extreme value theorem, which stated that the continuous function on a closed interval a,b is guaranteed to have both a minimum and a maximum within this interval. And even states that those two values happen either within the interval or on the endpoints. Now, Rolle's theorem, named after the French mathematician Michel Rolle, gives the conditions that guarantee the existence of an extreme value in the interior of a closed interval. So this guarantees the existence of this extreme value. So what this is suggesting is, if we look at here this picture, is that if we have a graph and the value of the graph at A is D, and if you go through the function and the endpoint of this function is at B, and the value of at B is also D, meaning that they're the same. So what it states is that at some point in the graph, you must have turned around, right? If those two are the same and you were increasing, at some point you must have turned around to get back down to the same value, right? It also works backwards. If you were at A and you went down, at some point, right? At some point, something must have happened to, and you have come back. But at some point, that point where you turn around, then you must have a horizontal tangent line there. Now, this is assuming, of course, that the function is continuous. Otherwise, we could have had a jump there, right? We could have just gone like that, and then boom, jump, you're over here. Also, that is differentiable on the closed interval a to b, because that way, if we're guaranteed that there's going to be a tangent that is going to be horizontal, then that means the graph has to be differentiable, right? So that's what we're saying here. So let's read this theorem. Let f be continuous, and we already talked about why it needs to be continuous, on a specific closed interval a to b, so we can guarantee to have the endpoints, and that is differentiable within the open interval ab. Then if f of a and f of b are the same, then there exists at least one moment, which is c, between a and b, such that the derivative has to equal 0, right, at c. So from Rolle's theorem, you can see that if the function f is continuous on the closed interval and differentiable on a, b, and if a and b are the same, f of a and f of b are the same, then there must be at least one x value between a and b for which the graph f has a horizontal tangent as shown in the figure. Now, if the differentiability part of the theorem is removed, then you can still say that there is a you can guarantee that that's going to be a horizontal tangent. You're going to have a horizontal tangent between a and b, but what you can say is that there's going to be a critical number, right? And now we can see that in the picture B. If you remove this continuity, at least you know there's going to be a relative max or relative min, right? Same thing here. You're guaranteeing that there will be a relative max or a relative min. Now, if you guys notice, I said or, because we don't know, right? You can have maybe one of each or none of each, right? So it depends on the function. All right, so let's do an example here that illustrates Rolle's theorem. Find the two x-intercepts. Find two x-intercepts of f of x squared equals 3x plus 2, and show that f prime of x equals 0 at some point between those two x-intercepts. So we can see the picture that was going on, right? But let's assume that we don't have a picture. But what we're going to do is we're going to find these two x-intercepts, right? X-intercept means that the function is intercepting the x-axis. Now, what do we know about the function? The value of the function is going to be This is 2, 1, 0, right? The function is 0 at x and an x-intercept. So we're going to let the function be 0 and solve for x by factoring the function and then using the zero factor property. This will give us x equals 2, x equals 1. Alright, now those are the two x-intercepts. That's that x-intercept, that's that x-intercept. And we have found those two. Now we want to show Rolle's theorem between those two. Now we know that they both equal each other, so we have satisfied this condition, f of a f equals f of b. But what we have to show now is that the function is continuous on this closed interval, which is because f of x is a polynomial, and we know polynomials are continuous everywhere, so definitely it will be continuous on any closed interval. In the same argument, we can say that the derivative of f is going to be continuous. If we notice, the derivative of f is 2x minus 3, which is also a polynomial, and we know that that f of x is differentiable because it is a polynomial, and so therefore we have satisfied this condition. So f of x is differentiable, and so on this open interval. All right, so now the question is, can we find that there exists a value between 1 and 2 where the derivative is 0? And what we're going to do, the strategy we take is we take the derivative of it, right? We take the derivative of it and we just set it equal to that condition. That's kind of like nice in mathematics. If you want to find when the derivative is equal to 0, then take the derivative and set it equal to 0, and then let the algebra do the hard work. And so what we're going to do is we're going to go ahead and add the 3, divide by 2, and we get x equals 3 halves. So by Rolle's theorem guarantee that this was going to give you an x value between 1 and 2. And we did, right? We found that value, x equals 3 halves. So Rolle's theorem guaranteed us, or it will give us our money back, that we will be able to find this x value. And so we did. And we can see the picture here that at f prime 3 halves is equal to 0. And we see the horizontal line there, right? The horizontal tangent line. And it is between 1 and 2, between the x-intercepts. Here's another example illustrating Rolle's theorem for the function x to the 4 minus 2x squared. Find all values of c in the interval -2 to 2 such that f prime of c is equal to 0. So let me jump in to the end of the page here. And so what we're going to do is first show the conditions that need to be met in order for us to use Rolle's theorem. So the first one is are there 2 points, are the two values where the functions are equal to each other. And if at f -2 we can have functions equal to 8, and at f of 2 positive 2 is f of 2 is equal to 8. So they both equal each other, so that means one of the conditions. The other condition is f has to be continuous, and it is because f is a polynomial, so it is therefore continuous everywhere. So it must be continuous on a closed interval, and f is differentiable because f is a polynomial, right? So those are the conditions we had to talk about before. So now we have met all the conditions, so that means that they're guaranteed to find an x value between negative and 2 such that the derivative of it is equal to 0. So what we're going to do now is find it. So what we're going to do is set the derivative equal to 0 and let the algebra do the work, and the algebra will actually find us that number. So factor the factor 4x from both terms, and that gives us x squared minus 1. We have this is gonna by the zero factor property suggest that 4x equals 0 and x squared minus 1 equals 0, and that will take us that location right here, and this will give us this condition right here. And then we're gonna solve for each one. Well, this is already solved, x equals 0. The second one, x squared minus 1, will equal 0 by adding 1 over here and then taking the square root on both sides. plus or minus square root of 1 is plus or minus 1. So we have x equals 0, x equals 1, and x equals negative 1. Now if you guys notice, x equals 0, x equals 1, and x equals negative 1 are within the interval. So we have found in this case 3 values of x for which f prime will be 0 by using Rolle's theorem. Now remember, Rolle's theorem only guarantees us that there will be this value. It doesn't actually tell us how to find them, right? We actually just use sort of a algebraic approach to find them. All right. The next topic, the next objective is to talk about mean value theorem. And the mean value theorem comes from the word of mean, which is average. So you're looking for the average value of the function. So if f is continuous on the closed interval a, b, and differentiable on the open interval a to b, then there exists a number c between a and b such that f prime of c will equal to the average value. All right, so what we're saying here is that if we meet all these conditions, that you can find a c between a and b that would equal to the average value of the function. So let's think about this problem. The next example gives us a problem where we can discuss this approach. So given the function 5 minus 4 over x, find all the values of c in this open interval 1 to 4 such that c in the derivative will give you f of 4 minus f of 1 over 4 minus 1. So that means that we can find that c. Well, first we have to show that f has to be continuous, and it is, because it is continuous everywhere and differential everywhere except at x equals 0, because we can see here that will make the function undefined. But we actually restricted the interval to be within 1 and 4, so that removes that case where the function would not be continuous and differentiable. So therefore it is, right? So if f is continuous between 1 and 4, so that means it meets the condition of the mean value theorem. So now it says that we could find this c value that would equal f of 4 minus f of 1 over 4 minus 1. So f of 4, by plugging in 4 in here, will give us 5 minus 1, which gives us 4. If we plug in 1, that will give us 4 over 1, which is 5 minus 4 is 1. And then over 4 minus 1, and that will give us 4 minus 1 is 3, 4 minus 1 is 3, so 3 over 3 is 1. So what we're looking for is a c value that when you take the derivative, that will give us, when you plug it into the derivative, it will give us 1. So there exists a c between 1 and 4 such that f prime of c equals 1. How are we going to do that? Again, what we're going to do is we're going to set the derivative equal to 1. So sort of what I explained before, right? If you want to find something about the function, when a function equals something, then just set it equal to that. So by the mean value theorem, we could find this x value by setting it equal to 1. Now, I want to solve this equation, and it's just pure algebra. So we'll do the cross product, x squared equals 4. Take the square root on both sides of the equation. Take the square root on both sides of the equation. And that will give us x equals plus or minus 2. So we have found two cases where the derivative of the function will equal 1. But we only were looking for values that were within this interval, so we have to check, and then we notice that -2 is not within that interval, so the only number that will satisfy this will be c equals 2. So c equals 2, f prime of 2 will give us 1. We can see here that the sort of the logic behind it. The average value of the function will give us sort of this the slope of this, and then we can say that if we move this to the end, at some point this will be the tangent line of some point, and that's what we got. Now this mean value theorem is very applicable, and in one of the cases here we're going to use that in practice 4. All right. Also, another use of the mean value theorem, if f is continuous on a closed interval a to b and differentiable on an open interval a to b, then there exists a number c between a and b such that f of b equals f of a plus b minus a f prime of c. Now, if you notice here, this actually is the same formula that you had over here. Is just when you solve for f of b. So you can find a value of b if you know the slope, you know b, we know a, and f of a. And this is a number, an equation that is coming to use in the future calculus courses. So you guys will see this later on. All right. Keep in mind that polynomial functions, rational functions, trigonometric functions are all differentiable at all points in their domain. So you guys want to keep that in mind. Maybe highlight this, keep that handy. If you guys ever have trouble figuring out whether a function is differentiable, this is a reminder, right? It's a great reminder. All right, so let's think about practice problem 4. Let's find finding an instantaneous rate of change. Remember, instantaneous rate of change means the velocity at that single moment. So if we're given two stationary patrol cars, and you guys can see that in the picture, one right there, picture over here, right? And they're equipped with radars, and they're 5 miles apart, so we can see 5 miles apart on a highway, as shown in the figure. As a truck drives by the first patrol, the speed is clocked at 55 miles per hour. So the speed is 55 miles per hour. Then 4 minutes later, the other patrol, the truck passes the second patrol 4 minutes later at a speed of 50 miles per hour. Now, in this case, it seems like, you know what, independent of each other, it seems like the truck is driving with the speed limit, right? But if they both have a sort of communication between them, and they notice that, you know what, 4 minutes ago it passed my partner, then can we figure out what was the average speed of this truck? And that's what we're gonna do. So prove that the truck must have exceeded the speed limit of 50 miles per hour at some time during the 4 minutes of driving between the two patrols. So let's say the speed limit is 55 miles. We're going to show that it actually was driving at 75 miles per hour. So what we're going to do is we're going to use the mean value theorem, right? So let's review real quick. We are talking about velocity, and so velocity is the derivative function of the position function, right? So velocity function is the derivative of the position function. So we can say that s of t will be the position function. That's usually how we denote it, right? And we know that position functions are continuous and differentiable. So that sort of meets the condition between 0 and 4. The question was so the question is what's the average velocity? So we can figure out the average velocity between from the 2 points. Now, in order for us to find the average velocity, we need to plug in time in there, and we're gonna have to plug in the time there. Now, they give me 4 minutes here as the time between the two patrols, but the velocity is actually in terms of hours. So that's inconsistency. We need to be consistent. So what we're going to do here is we're going to convert the minutes first into hours. And I remind you guys that that's something that we can easily convert by thinking about, okay, 4 minutes times the value of 1, right? This is technically 1 because 1 hour is equal to 60 minutes. So the way we do is going to be the minutes down under on the denominator and the hour on top. So 1 hour is equal to 60 minutes. That way the minutes will cancel each other out, and now you have 4 times 1 hour over 60 gives you 1/15 of an hour. All right. So 4 minutes is 1/15 of an hour. So what we're gonna do is we're gonna plug it into the position function, and we're gonna minus the position function at 0, and then all divided by the time, which is at 1/15 of an hour minus 0 hour, right? And then now, what is the position at 1/15 of an hour? Well, they told us that that was 5 miles away. Assuming that this is time 0, that means you have driven 5 miles away. So that's your position. Now the position at time 0 is 0. On the denominator, we have 1/15 minus 0, which is 1/15. 5 over 1/15 is the same thing as having the product of 5 times the reciprocal of the denominator. So it will be 5 times the reciprocal of 1/15 will be 5 times 15, which equals 75 miles per hour. So this is equivalent to the derivative of the derivative of time, right, at some point. So which we know is your velocity, which is your velocity. So we're saying the velocity of the truck between some point between 0 and 4 is going to be 75 miles per hour. So you can come to the court, and assuming that the truck didn't jump into a spaceship and jumped space, we can say that the truck went over the speed limit. So we can say that without doubt, the truck was speeding. All right, so the velocity of the truck at some point it was 75 miles per hour. All right, I hope this is helpful, and I hope you guys find it useful, and let me know if you guys have questions. Thank you.